Welcome to the 11th lecture for Radiochemistry 702. This lecture is on the application of nuclear material. It's in two parts, and the readings for both parts can be found here in Nuclear and Radiochemistry, Chapter 11D, and Modern Nuclear Chemistry, Chapter 4-10. The outline for the first part is shown here, where we'll talk about isotope production methods, neutron generators, ionization sources, and heat sources. The second part will cover radiopharmaceuticals, example shown here of radiopharmaceuticals, and we'll discuss both diagnostic, where gamma emission either through the decay of an isotope, or positron emission tomography, where a positron annihilates an electron and produces two photons. We'll also talk about therapeutic radiopharmaceuticals, where the particle emitted is used to induce cell death into normally a cancerous cell. Diagnostic radiopharmaceuticals, the number one used radiopharmaceutical isotope is technetium-99m. And for therapeutic, we'll discuss a number of different types, both beta emitters and alpha emitters. For the upcoming lecture, the isotope production methods will be an extension of lecture 8, where we discuss isotope production methods with accelerators, and in this case we'll go into a little bit more detail about some specific isotopes that are produced. One primary route for the production of isotopes is through the fission process, and there are two main methods in producing isotopes of use through fission. One is through the direct production of fission products, in which the fissioning of the uranium-235 itself creates the isotopes of interest. Another is the formation of new isotopes through neutron reactions. As an example, plutonium isotopes are produced in this route, so one can do successive neutron capture. Plutonium is formed through capture on uranium-238, that forms uranium-239, that beta decays to neptunium-239, beta decays to plutonium-239. One can use this route to continue up capture on plutonium up to americium, curium, berkelium, californium. So you can go all the way up to californium and isotopes such as californium-252 from this route, and we'll see that there are a few isotopes that we use, such as plutonium-238, which can be produced from the neutron capture of neptunium-237, and americium-241, which again is from the successive capture to plutonium-241 and then the beta decay plutonium-241 up to americium-241. An overview of the fission process is shown here, where a uranium-235 encounters a neutron, forms an excited uranium-236 state. This undergoes fission, releasing more neutrons, which can then be used to induce another fission. And the main driving factor for this is the large neutron capture cross-section of uranium-235. As you see, here's the capture cross-section of uranium-235 as a function of neutron energy. These thermal neutrons have a large neutron capture cross-section, and as comparison, uranium-238 we see only starts having significant neutron capture cross-section on the order of 1 MeV. The direct formation of fission products from the fission process is shown here, where elements from a Z of 34 selenium all the way up to dysprosium of about Z of 66 can be produced, and that's shown here, fundamentally the middle section of the periodic table. You can produce isotopes with different yields by the fission process. And here are shown some different yields for fission products as a function of fissile isotope. The green here is for uranium-233, the red is for uranium-235, and the blue is for plutonium-239. There is one trend that's seen here, is that the high Z peak is fairly constant and the low Z peak varies. So for instance, if one wants to make molybdenum-99, the fission process has a fairly high yield, and that's why fissioning of uranium-235 is used to produce molybdenum-99, which then decays into technetium-99m. We'll discuss that in a little bit more detail in this lecture. One can also vary the fission process slightly by changing the energy of the neutron. One what's shown here is the fission process for thermal neutrons versus the fission process for fast neutrons. The peaks don't change dramatically. There's a little bit of decrease in the higher peak. What is noticeable is the increase of the valley peak. So there is some influence on fission product properties and relative yields based upon the neutron energy, the fissile material. So one can use that, but primarily fission products are produced by fissioning uranium-235. And fission products, since they come from heavy elements, tend to be neutron-rich isotopes, which undergo beta decay to form stable isotopes. So molybdenum-99 beta decays to technetium-99m, which then goes to the ground state technetium-99, which will then decay to ruthenium-99. So for isotopes produced by the fission process, they're neutron rich. When they decay, they move up the periodic table. Another route for producing isotopes is by accelerators. And what's shown here is a schematic of an acceleration process where deuterium is impacted upon nitrogen, an excited oxygen isotope is produced, which can then undergo decay by neutron emission, alpha emission, a neutron plus a proton, de-excitation, tritium emission, a range of different emissions developing into a range of different isotopes. One can tune these reactions by changing the energy. An example here's the reaction cross-section for a proton on oxygen 18 producing fluorine 18, which is a useful radiopharmaceutical. And as one can see that one can increase the reaction cross-section, so the probability for the reaction, by tuning the particle energy. So you can tune the target material, you can tune the particle, you can tune the particle energy. So you can use these techniques to vary and produce specific yields of isotopes. An example here is this is the very first cyclotron that was produced by Lawrence, very small handheld. This is a typical route how a cyclotron operates, where a charged particle is introduced into the center. These magnetic field sectors vary. They accelerate, push, and pull the particle, and by the time it hits a certain known distance, it has to be going at a certain energy based upon its mass and charge. Accelerators are generally used for the production of neutron-poor isotopes. For instance, fluorine-18, the stable isotope being fluorine-19. Accelerator-produced isotopes tend to decay by either electron capture or positron emission. For many radiopharmaceutical applications, it's the positron-emitting isotope that's of interest. Now, it is possible to produce neutron capture with accelerators by having an accelerator hit a beam stop that produces neutrons, and then using those neutrons as neutrons for reactions where neutron capture occurs. So accelerators can be used to produce a range of isotope, but they're primarily used for neutron-poor isotopes that undergo positron emission. The first set of isotopes to be discussed are those involved in neutron emitters. So these are small sources that are designed to produce neutrons, and these neutrons drive reactions that can be used to determine something about a material. For instance, elements in a sample can be based on reactions with neutrons. Small sources can be used for detection of sodium or actinides. These neutron emitters are also used for evaluation of subcritical amounts of fissile material. They can probe the amount of neutrons that are produced by adding neutrons in a subcritical configuration. This is a useful capability, and these small sources can be used to determine if subcritical amounts of fissile material are in configurations that need to be remediated or treated to prevent any criticality. These neutron emitters are also used to detect water or hydrogen by neutron backscattering. So neutrons, very sensitive to low Z material, particularly protons, hydrogen. They can be used to detect the presence of water. For instance, they can be used in drilling activities to determine if water is present or oil would be present. And finally, neutron emitters can be useful for detection of explosives. There are two routes that this can be done. Both utilize cross-section resonances for nitrogen and oxygen. So when we mention resonance cross-section, those are the higher energy neutron cross-sections. There are some very high resonance cross-sections for nitrogen and oxygen. Explosives have a characteristic nitrogen to oxygen ratio. They tend to have high amounts of nitrogen to oxygen. And these cross-sections can be used to measure characteristic gammas that are produced from a neutron being absorbed by nitrogen or oxygen, then that excited state de-exciting, emitting a neutron, or from the absorption of the neutrons as it travels through the material. So imagine if you had the ability to measure the amount of neutrons that were traversed a certain sample, you could see that certain energies would be decreased. These energy ranges could correspond to nitrogen and oxygen, thereby determining, using this as a route to determine the amount of nitrogen to oxygen in a sample, and understanding certain ratios would be characteristic of an explosive material. These explosives can be used, this explosive detection technique can be used, one would think about it for material that's being, for instance, brought in through a port. You can evaluate a container for explosive material, or you could use this technique to determine buried explosives such as landmines. Example of isotopes that are used as neutron emitters are provided here. Possibly the simplest one is just a californium-252 source. The decay data for californium-252 is shown here. It has a half-life of 2.645 years. 96.9% of the time the californium decays by alpha. However, 3.11% of the time it decays by spontaneous fission. It's this spontaneous fission branch, and if you look at isotopes, this is an incredibly large spontaneous fission branch for this sort of isotope that also decays by alpha. This large spontaneous fission branch for this relatively long-lived isotope gives rise to a sufficient amount of neutrons that can be used as a detector. So to determine the amount of neutrons that one could produce, it averages between 2 and 3 neutrons per emission per decay. That results from spontaneous fission for californium-252. So one can determine the activity of your californium-252 knowing that around 3% of the time it decays by this spontaneous fission, which then results in the multiple neutrons. Another route for neutron emitting isotopes is to combine an alpha-emitting isotope with beryllium. The reaction shown here of an alpha particle on beryllium-9 producing carbon-12 with the emission of a neutron can be exploited as a neutron emitting source. A number of different alpha sources can be used: americium-241, plutonium isotopes, or polonium isotopes. Shown here is the cross-section for the beryllium alpha reaction, and as one sees that the high cross-section of around half a barn is achieved with an energy close to 4.5 MeV. This is a very common energy range for an alpha decaying isotope. So alpha decaying isotopes are good for energetically for producing this reaction. And here's some data here on evaluation of different beryllium type of targets with a yielded number of neutrons per alpha. You see those values are on the order of 3 times 10 to the minus 5. There's not a huge dependency on the beryllium chemical form, and as you do see that you do need quite a few alpha particles to produce one neutron. So this would mean that your isotope activities would need to be high, and you could use this ratio if one wanted to determine, if one wanted to produce a neutron emitting isotope with a neutron emitting source with a certain amount of isotope, certain amount of neutron production rate from that isotope. Using these factors, one can determine what activity would be necessary to produce a neutron source of a given neutron yield. Another set of utilization of isotopes is exploiting the emitted particle of the isotope for a use. An example is smoke detectors. Ionization smoke detectors use an americium-241 source. This americium is in the form of the oxide. It has an activity on the order of 33 kilobecquerel, and this works by using the alpha particle that's emitted from the americium-241 as an ionization source. So basically, when smoke is detected, when it enters an ionization chamber through this route. When smoke is not present, alpha particles ionize air that's in the ionization chamber. These ions they travel in the chamber, they create a low current, which is detected by the ionization chamber. When smoke enters the ionization chambers, any ions that are formed by the alpha particle can be attached to the smoke. They no longer go to the electrodes in the ionization chamber. The current drops. This decrease in the drop of the current triggers the alarm that indicates that smoke is present in the smoke detectors. One route that is commonly used is to have a sealed detector and an open detector, so that the sealed ionization detector of the ionization chamber does not have the smoke particles going through it, so that changes from that current, the sealed current, to the open current are what's used to trigger the alarm that indicates the presence of smoke. Another particle type interaction is explosive detection. This is what's commonly used when one travels through an airport. If the baggage is swiped and they're looking for explosives, they actually use a nickel-63 beta emitter, and the method is ion mobility. So the sample that's swiped is placed over a nickel-63 source. This ionizes the molecules that are collected on that source. They enter an ion mobility chamber, so after the sample is collected, it's placed on top of the chamber. The reason that this method is chosen is because of the sensitivity. One can detect explosives down to picogram levels. The molecules are ionized by the beta particles. The degree of ionization is related to the size of the ion and the shape of the ion, so you can think of it as a physical cross-section that the molecule has in the presence of the ionizing electrons. Once ionized, the ionized molecule then enters the chamber. The chamber is partially filled with a gas. The pressure can be varied, but you have a drift gas. The molecules then move along the ionization chamber, and they separate within this drift gas. They're detected at the end, and the migration time for the molecules in the ion mobility detector are characteristic of that molecule. So one can perform this evaluation and gauge upon the times that are for those molecules that are indicative of explosives. And this is the technique that's used in airports worldwide for detection of explosives on baggage. The isotope plutonium-238 has applications due to its thermal properties, which shown here are a little bit more than half a watt per gram of plutonium-238 material. This is due to its relatively short half-life of 87.7 years and relatively high energy alpha decay. Plutonium-238 can be produced two routes. One is neutron capture on neptunium-237, producing neptunium-238, which then undergoes beta decay to produce the plutonium-238. The produced plutonium-238 is then separated from unreacted neptunium, or a curium-242 source can undergo alpha decay to produce the plutonium-238. These power sources are often used for space exploration. The plutonium is generally in the form of an oxide with the isotopic concentration plutonium-238 equal to or greater than 83.5%. The oxide source is actually enriched in oxygen-16 to limit the alpha N reactions that occur from oxygen-17 or oxygen-18. As an oxide, the plutonium-238 oxide has about 0.4 watts per gram. A heat source or a thermoelectric generator for space exploration is generally on the order of 150 grams of the plutonium dioxide, up to 83.5% of it being plutonium-238, and it's usually contained in an iridium container. The overall route with some specific additions for the production of plutonium-238 is shown here. In the United States, it was made in Savannah River by irradiating neptunium dioxide particles that were embedded in an aluminum matrix. This was then dissolved in nitric acid, and through high nitric acid concentrations, separation of neptunium from plutonium was achieved. First, the neptunium-plutonium separated out any fission products that might have resulted due to the fissioning of the actinides with fast neutrons, and then the neptunium was separated from the plutonium. What was done specifically is that these aluminum targets were dissolved in 10 molars nitric acid with a small amount of HF, and the nitric acid solution was treated to give a final concentration of 8 molar. Ferrous sulfamate was used to adjust the valence of neptunium-plutonium to the trivalent state. Remember, neptunium-plutonium can have multiple oxidation states, so to have consistent chemistry, both elements had to have their oxidation states treated. The first route for the separation was on a Dowix type 1 resin to separate the neptunium-4 and plutonium-4 from the aluminum and the bulk of the fission products. The second stage, the ion exchange, the plutonium-4 and neptunium-4 were again bound to the column, and plutonium was selectively eluted as the trivalent state using ferrous sulfamate as a reducing agent and hydrazine as a holding agent. Then the neptunium-4 could be eluted from the column, precipitated as the oxalate, and then reused as targets. The plutonium-238 was purified in the third stage of ion exchange and eluted as the nitrate, and then sent for further processing into the dioxide, generally through the same route where you would precipitate the oxalate, then thermally treat that. As an example, as we already discussed, 150 gram plutonium dioxide source is a little over 60 watts. These are then welded into containers, these tungsten iridium clad containers, and they can be used for either general purpose heat, or the heat is then used to produce electricity. These sources are called general purpose heat sources, since they can be used for a number of different applications. As an example, these sources, as shown here, relatively smaller amount, 1 watt of plutonium, shown here, are on the rovers that are doing Mars exploration. These do nothing more than provide heat, so that the rovers can operate when the sun is not present. Temperature on Mars plummets. If they had to wait for solar electricity routes as the only means of producing heat, they would not operate. So these sources provide constant heat that can be used to maintain the robots under Mars cold conditions. Radioisotope thermal generators are also an application of these heat sources. As shown here, the heat sources are introduced into these generators. The heat is then used to convert to electricity. The overall yield is not very good, on the order of 20 to 30%, but this does provide a constant electrical source without any moving parts. So you basically have this thermoelectric generator which utilizes the heat coming from the radioactive decay of the plutonium-238. An example of what that source looks like is shown here. This is on the Cassini space mission. They used 333 heat sources from Los Alamos National Lab. This was on the order of 40 kilograms of material, and it provided electrical power, where on the order of half a kilogram was used to just provide heat for spacecraft components. And what you can see from here is that the technician evaluating the dose from the sources shows that there's not much activity from these sources, and it's due to the fact that the plutonium-238 is primarily an alpha emitter, and the alpha decay is extremely well shielded. In fact, it's used to generate the heat, so there is very little dose coming from these heat sources. Another example of a space mission that utilizes plutonium-238 is shown here, the New Horizon that arrived at the Pluto-Kuiper belt mission. It had around 10 kilograms of plutonium with 1 RTG and a number of the heat sources. So plutonium-238 is a reliable material that can be used for generating heat, and then this heat can also be used to generate electricity for unmanned space missions. In the United States, there's current efforts to renew the ability to produce plutonium-238 for further missions by the National Aeronautics and Space Administration. This concludes the first part of Lecture 11 for Radiochemistry 702, where we discussed isotope production methods, neutron generators, ionization sources, and heat sources. Part 2 will cover radiopharmaceuticals. Please proceed to Part 2 when you've completed this lecture.